Now this is other new character of the waves we are getting, which is called string wave. Sometimes you will see if the two end of the string is rigidly support and you vibrate it, it's give you a frequency. Right? Practically, we observe this thing in the guitar, sitar, tanpura, such as this. If we suppose this take as a guitar, you are vibrating like this, and you put your hands like this way, you will see the vibrating string moves, the waves are coming back like this. That's why a guitarist always vibrate this direction, waves come this way, and superimpose takes place due to the reflections of the waves. Question in IIT basically will come from the reflecting nature of the waves and the string vibration, supporting rigid ends, elasticity module of the string, and the uniformity and density of the strings. All things will come in the law. See, if a string is vibrate in a particular points and is producing certain waves which is passing to the string formations, then frequency of the waves definitely, as we know, v upon lambda. V is the velocity of the string wave and lambda is the wavelength propagating waves. Velocity of the string waves is basically follow the simple analytical law is under root of T upon mu. If the string is made of a uniform dense object, the density is uniform, then the velocity in the string wave is under root of T. T is the tension of the string. That tension is developed due to the rigid supports from both ends. So it's one of the most interesting and important things that the support in the both ends must be rigid. If it is loosed, definitely you cannot get the octave value. That's why before the operating the string, a guitarist always first rigid it in proper directions. And mu here is called the mass per unit length of the string. So that is another part which must be constant for a particular material for a constant length. Now, if string vibrate in different modes, such as if we like to get the sa, re, ga, ma, pa, dha, ni, sa, that is octaves in the string, so you have to vibrate different number of notes and antinodes. So in the first case, if we take a string and we vibrate with very small amount of pressure and respective length as large, if this is your string and rigid at both ends, and you are vibrating the string with certain external forces and the string vibrates like this. So definitely in this first case we are getting the frequency will be V upon lambda, that is V upon, this is your definitely length of the string is L, so this is your lambda by 2, so this become 2L. So this frequency as per the velocity law we can write down 1 by 2L under root of T upon mu. So this is called the fundamental frequency of the string. Three things we are depending. One is your length, second is tension, and third is your mass per unit length. What is this? We will come to the string law. But if we like to vibrate the string with a very large, in this case you are getting two antinode and three nodes. Here you are getting two nodes and one antinode. So here number of node is more than number of antinodes. You must remember this part also. In this case you are getting this is lambda. So frequency become V by lambda, that is V upon L, that can be written as 2 times of 1 by 2L under root of T by mu. So that will be called as second harmonic but fast overtone. If we like to vibrate the string with a large frequency, we will vibrate more. In this figure, we will get the more vibrating frequency, such as if this is your string and you are vibrating in 3 modes. and reflecting waves give the nodes and antinodes. In this case, you will get F3 is 3 1 by 12 V by T by mu in case of V. Then this is giving you third harmonic at second overtone. So very simply we are observing in the string the frequency ratio becoming 1:2:3. But for the fundamentals concepts with frequency we can write down Fn for the string is n times of V by 12. N is here, definitely must remember the number of superposition or number of antinodes. So this is number of antinode. So this law is modifying as a string law, such as we are getting in a string wave producing the frequency which is basically 1/12 under root of T by mu. If P number of superposition takes place, that is P number of antinodes is producing, so it's become Fp is P/12 under root of T by mu. P is the number of antinodes or loops. And another things we are getting, the frequency ratio F1 is to F2 is to F3 as long as you go is 1:2:3 as long as you go. Interestingly, whatever other things we are getting, that is number of antinode is equal to number of node minus 1. And third point, how the density of the wire, elasticity of the wire and the length of the wire will affect, or the radius of the wire will affect. That's why you need the modification of this law, such as this law can be modified as F is 1/12 under root of T is there, mass per unit length means mass can be written as volume into density, that is we can write down pi r square L into rho, that upon L. Move it, L and L will cancel each other, formula becoming very simply 1/2 L r under root of T upon pi rho. So from these particular things, again we are observing the frequency is directly proportional to under root of tension, inversely proportional to the under root of length, inversely proportional to radius, and inversely proportional to under root of density. This is the simplest way to get the question in your AIEEE or simple medical test. But what will happen if the temperature increases in this function? What will happen if the density is non-uniform? What will happen if the temperature increases the length or area or both? So question for IIT level of entrance, we have to modify it, or we have to originate another laws or supplementary laws for the questioning of the strings, and they are like this.